I'm very happy to be back in College Station. It's a beautiful town. I'll be talking about my work, which really lies in between sort of physics and mathematics. And I know very little of both things, but somehow there's this interface where you can work at and really make progress. And I would like this talk to be introductory and accessible to everybody, so please ask me questions.
I actually have a comment. There's a laser pointer waiting for you right on the other side of the table.
On the table?
No, right here in the front.
Oh, it's right here.
Yes.
Okay. This is on the right side. This one was on the table.
Right on the table.
I was thinking about the other side of the table, which would be the bottom side.
The English language is such a beautiful thing.
Okay.
Right. I will not interrupt any further. Sorry.
Yeah. So please ask questions. Cool. So my talk will be about Calabi manifolds, which is like a mathematical subject, and gauge theories, which are physical, and the interplay between these two things. Okay. So just to start, here's a definition of a Calabi threefold. It is simply connected, meaning no one cycles, non-trivial one cycles. Compact, which means finite, non-infinite volume. Kähler manifold, which I'm not going to explain. Of complex dimension 3, which has a nowhere vanishing holomorphic 3 form. Okay, so what that basically means is, if you think about it in as a real 6-dimensional manifold, then the connection, the Levi-Civita connection, has SU3 homogamy, okay, and it's simply connected, and that's equivalent to this definition. And in this talk, we will focus on the type 2 string theory on 4-dimensional Minkowski space times a Calabi threefold. Okay, and that's X. X will always denote the Calabi threefold. And we will work at tree level in the string coupling, which means, as far as the worldsheet is concerned, I'm always working on a sphere. Okay, so that's and as always with string theory, there is always two perspectives that one can take. There's the worldsheet perspective and the space-time perspective. And as far as the worldsheet goes, we will be studying 2-dimensional 2,2 supersymmetric conformal field theories. And from the space-time point of view, it's 4-dimensional n equals 2 supergravity. Okay. And there's a nice map between these two things. So whenever you have a marginal operator or a marginal deformation of this SCFT, it corresponds to a massless multiplet in space-time. Okay. And so various quantities such as the moduli space metric translate into more familiar things like kinetic terms for these massless scalar fields. Okay. And what I find interesting about this whole business is that various geometric questions about Calabi manifolds can be used to answer these sort of more physical things. Okay. So that's what. Any questions?
What corresponds to the black holes in 2 supergravity in 2D safety?
Well, I mean, for that you need to have there are D-branes and various things that can wrap curves in this Calabi, and those can correspond to black holes with the supergravity point of view. Yeah. Any more questions? Cool. All right, so my main motivations are to compute these 4D effective actions that one gets from string compactifications. At genus 0, but taking into account alpha prime corrections. From the math point of view, this corresponds to computing the so-called Gromov-Witten invariants of Calabi manifolds, which are essentially counting invariants. Okay, they count the number of curves in a given homology class. Okay, so that's what these things are. And from the string phenomenology point of view, you might be motivated to construct new kinds of Calabi manifolds with certain properties. And more generally, if you're a mathematician or if you think about the string landscape, you might be interested in understanding the space of Calabi manifolds. Okay, so are there finitely many topological types? Is there some kind of classification of these things? And these questions actually feed back into learning more about string vacuum and also 2D superconformal field theories. And like I said, what I really enjoy is the interplay of physical and mathematical ideas. Okay, so they're often like these difficult mathematical notions that have very simple counterparts in terms of physics, and so it helps you, it helps you a lot. It's interesting.
Excuse me, regarding Gromov-Witten invariants, are they topological invariants?
No. So strictly speaking, there's a mathematical definition that I don't know, but roughly it stands for, if I have a given homology class, it counts the number of rational curves, at least at genus 0, it counts the number of rational curves inside that homology class.
But can you use such an invariant as part of the effective action?
Yeah, so it plays a role in the effective action, and I'll show you later on.
It contributes to amplitudes and everything. It's
exactly.
a genuine effective action term.
Exactly.
Okay.
So the way it contributes is by instant-on corrections. So I'll show it to you in like a couple slides. Okay, so here's the plan for my talk. So it's basically two parts. In the first part, what we will do is take a Calabi manifold that we already know about, okay, and we'll try to design a GLSM, which is a gauged linear sigma model. So it's basically a gauge theory, which will help us analyze the Calabi manifold and compute its properties. Okay, so that's the first part. So going from math to physics. And the second part is trying to see whether we can use physics to construct new examples of Calabi manifolds. Okay, so they're basically using gauge theories to try and see if we can construct new manifolds. Okay. Cool. So when we are studying string compactifications, especially of the type 2 kind, you start with a worldsheet theory that is a 2,2 nonlinear sigma model whose target space is the Calabi manifold of interest. Okay, and with the Calabi metric, this theory actually flows to a superconformal field theory, which has central charge, the complex central charge 3. The various aspects of the geometry of this Calabi manifold, namely the metric moduli, which can be divided into two kinds, the complex structure and the Kähler moduli. The Kähler moduli govern the overall size of this thing, and the complex structure moduli control the shape. Okay? And so in spite of this RG flow, these moduli, which refer to geometric things in the target, actually flow to marginal operators of the SCFT. Okay? So even though the metric gets corrected, the metric moduli persist. And the SCFT moduli space has the same structure as the moduli space of the Calabi. It's locally a product of these two, of a complex structure and Kähler bit. So now what I'm going to tell you is just a little bit about this complex structure and Kähler. It's not terribly important for the talk, but it's just to get you thinking along these lines. So the complex structure moduli space is the easy one. Okay. So what that means is that there are no quantum corrections we need to worry about. So you can just take the Calabi and do a math calculation, okay, and that is correct even at the quantum mechanical level. Okay, quantum mechanical as far as alpha prime is concerned. And so the complex structure moduli space has H21 of X, this is the Hodge number of moduli, and these moduli are given by taking the holomorphic 3 form of the Calabi and integrating it on 3 cycles. So that gives you a bunch of numbers, and these are called the periods, pi I. Okay? And the moduli space is such that these periods satisfy a linear system of PDEs with some generalization of regular singular points. Okay? So whenever an ODE has regular singular points, it means you can solve it. Okay? So what I'm trying to argue with this is that this moduli space is solvable, at least in principle. Okay? And if you wanted to calculate, so now let's say I had a string compactification, I had moduli from this complex structure sector, then I can calculate the space-time effective action very easily. Okay, and it's given by this formula. So e to the minus k is given by taking the holomorphic 3 form, merging it together with the anti-holomorphic one, and integrating it on the Calabi. Okay, so that's it. So this is solvable. So are there any questions?
Are there G-string corrections to complex structure?
Yeah, so it depends whether it's 2A or 2B, and I forget. But yeah, there can be G-string corrections in one, and there aren't G-string corrections in the other. And that's because like G-string is in some either a hypermultiplet or a vector multiplet, and these moduli lie in the other one. You know what I mean? So, yeah, so depending on 2A or 2B, there are no G-string corrections, or there are.
2 quick questions. Is it obvious to show that there are no alpha prime corrections to MCF? How difficult is it?
I'm not able to think of it at the top of my head right now, but I think yeah, I can't think of it right now, but, but it's a standard thing which, you know.
There's some proof of this,
yeah,
which is not utterly trivial. Okay.
Yeah. So
And
essentially the way it comes about is because you have a two-dimensional world sheet, and for this complex structure modular space, you're thinking about 3 cycles, and so the world sheet doesn't really fit in with the 3 cycles. So there's some loose sense, okay, but I don't know the actual.
Okay. Verma, the second question is this formula at the bottom.
Yeah.
This is with the assumption that there are no other moduli, right? If you turn on the Kähler moduli, how will this be modified? Are you going to show us when they are both in action?
Yeah, so locally, when you're thinking about supergravity at least, it's going to be 2 separate terms. So the Kähler moduli, in the space-time effect of action, the Kähler moduli are not going to interact with the complex structure moduli. So it's going to be 2 separate moduli spaces.
But if I want to know what's the Kähler potential in the effective theory in 4D,
yes.
Will this be the formula?
It'll be this, and then there'll be another term for the Kähler moduli, which I'm going to show you in the next slide. Okay, so this is the Kähler moduli space. I guess I don't show it to you. It comes up later on. I'll show it to you.
Okay.
But yeah, so the Kähler moduli space is a slightly different story. You know, you have H11 of these moduli which are complexified by the B field. So you have H11 complex moduli, and this moduli space receives instanton corrections. Okay. Now it's because H11 is kind of 2-dimensional, and so anytime you have a holomorphic curve, then the world sheet can wrap on that curve and give you an instanton contribution, which is given here. So let's say you were computing a correlator of 3 H11s. You know, you would have a classical piece which you can calculate from geometry. And then you have these instanton corrections, the coefficients of which are these Gromov-Witten invariants. Okay. So the Gromov-Witten invariants essentially count the number of different types of instanton corrections that you can get. And so in order to calculate either this correlator or the Kähler potential on this moduli space, you need to know these numbers. Okay, but these numbers are tough to calculate. Okay, but you can use, so you know, mirror symmetry is really important because by constructing a mirror to this Calabi, you can realize the Kähler moduli space as the complex structure moduli space of a mirror, and because the complex structure one is easy, you know, we can use that to calculate these Gromov-Witten invariants. So that was the approach, that is an approach used to calculate these numbers and thereby infer what the Kähler potential is. Okay, but that requires you to be able to construct a mirror manifold for the Calabi that you're interested in. So if you can do that, then you can calculate this easily. And what I'll show you in the talk is how you can avoid that. Okay. Are there any other questions? All right, so let's turn to gauge linear sigma model. So these are the main sort of physicsy things in this talk. And the basic idea is very simple. Even though I've attributed it to Witten, it goes before Witten. So the basic idea is whenever you have a nonlinear sigma model that flows to an SCFT, you can construct a different UV fixed point, which is a gauge linear sigma model, which has linear kinetic terms, and it's a free fixed point that flows to the same SCFT as the nonlinear sigma model. And so all the infrared properties can be studied using this theory, which is simpler rather than this theory. Okay?
So GLSM is not on shell equivalent to an LSM?
It isn't. It isn't. So actually an easy, so actually the reason I said it goes before Witten is because a great example is the pion Lagrangian and QCD. Okay, so they're both very different in the UV, but ultimately they describe the same scattering effects of pions. Okay.
I thought there are some auxiliary fields in GLSM which, when eliminated, it gives you an LSM. Apparently, that's not the case.
No, that's not the case.
Okay.
Do you have a higher dimension example of this scenario?
Of this?
Yes.
Like QCD and the pion Lagrangian. Okay, so here you have a free theory of pions that interact. And one side is the nonlinear sigma model. This is the coset theory that you write down for symmetry breaking. And here, the gauge linear sigma model is literally QCD. Okay, so that's a gauge theory where you have free fermions and gauge fields. So it's UV free, and then it flows to this thing. So that's the basic idea. So it's not really that big of a leap, but in 2 dimensions, there are lots of cool things that one can do. Okay. So essentially, so if you want to study a Calabi, what you want to do is design a gauge theory that flows to the same SCFT as the nonlinear sigma model for X. Okay. So once you do that, you can start calculating its properties. Okay, and just to write down Lagrangian really, let me tell you about 2,2 supersymmetry. It's essentially the dimensional reduction of n equals 1 supersymmetry in 4 dimensions. So the multiplets look familiar. There's a chiral multiplet that has a complex scalar fermions in F, a vector multiplet where you have the gauge fields and the D term. And in here, you also have a complex scalar. Okay, so that's the gauge fields in 2 extra directions that are compactified and become a scalar here. And in 2D, you can also write down a twisted chiral multiplet, which has no analog in 4 dimensions, where you have a complex scalar, and a D term. And so essentially, the twisted chiral is the field strength multiplet for the vector. Okay. So
and what is V01?
Say it again.
V01. What is that?
So that is basically the field strength.
Oh.
So it's F mu nu. So if V is your vector field, V01 is basically the field strength, which is F V. That's why I've written V01. Because in 2D you don't have any other. The antisymmetric tensor is just epsilon mu nu. So it's V01.
Sigma is the ordinary field. It's not a field strength.
Sigma is just a complex scalar.
Complex scalar. V01 is field strength. Okay.
Yeah. Cool. And so to specify a Glsm, you have a gauge group, and you have some matter, which is chiral multiplets in some representation R, and you can write down the following action. Okay. So this is familiar from 4D. This is this is just the matter multiplets interacting with the gauge field. This is the field strength, where sigma is a twisted chiral, and you have a superpotential, which again is similar to 4D. And again, what's new in 2D is that the Fi term can be written as what is called a twisted superpotential. Okay, so this d2 theta tilde, so basically it becomes a second holomorphic type quantity, just like the superpotential. Okay, so this thing, the twisted superpotential is a holomorphic function of the twisted chiral fields.
Well, what's theta tilde?
Where? Oh, theta tilde. Theta tilde is theta plus theta bar minus. So here, the superspace variables are theta plus theta minus, theta bar plus theta bar minus.
Mm-hmm.
And so this one just has theta plus theta minus.
Mm-hmm.
This one has theta plus and theta bar minus.
Uh-huh.
Or the other way.
Okay.
Cool. So, when you're interested in GLSMs that flow to conformal field theories, what you try and do is preserve the vector and axial R symmetry in the UV, so that when it flows, it becomes the U1 left, U1 right, superconformal, the currents of the superconformal algebra. Okay? And so wanting to preserve this condition tells you that the superpotential W must be quasi-homogeneous so that you can have nice R charges, and there's an anomaly condition on the axial current, okay, which looks like that. And so if you have these conditions, the GLSM flows to an SCFT, and now the marginal parameters of the SCFT, which is what we want to study, the moduli, are basically the coefficients of the superpotential, W, and the Fi parameters and theta angles. Okay, so this parameter C is basically the complexified Fi parameter, which are combinations of the Fi parameter and the theta angle. Okay, so these basically become the Kähler moduli. These are like the complex structure moduli.
Excuse me, I think psi, but where does theta enter, this formula, theta angle?
The way it enters is because you have this V01, which is the field strength.
Uh-huh.
So the way the Fi term enters is R times D. And so the way the theta angle enters is theta times V01.
But I don't see it in the formula below, in the action, do I? It's not.
Well, that's because I haven't written it.
It's hidden.
It's
In which
because
term is
C-
it hidden? Yeah.
So C is R plus I theta,
Okay.
roughly. Cool, great. And so the basic procedure, as I said in words already, given a threefold, you want to design a GLSM, then you try and calculate the vacuum moduli space of this SUSY gauge theory, okay, as a function of the FI parameters. And then you check that in some limit of these parameters, you get back you get a nonlinear sigma model. Okay, so that's the check. So that's the whole GLSM business. This is what we want to try and do, at least in this 2,2 Calabi context. Okay, and here's a canonical example, and I'm going to go through it quickly. So, for example, if you want to design a GLSM for the quintic Calabi, what you would do is have chiral fields, have 5 chiral fields with charge +1 and a single field of charge -5. Okay, and you have a U1 gauge theory with this superpotential, P times G5 or 5. Okay, and this is the twisted chiral superpotential. So, so when you take this GLSM and analyze the D terms and the F terms, okay, what you realize, and I won't go through this because I realize that I already spent a long time on the first few slides. That when you make R very large and positive, the phi fields are non-zero, and what happens is that this P field, which really is some kind of Lagrange multiplier, okay, enforces the constraint so that the vacuum moduli space looks like this. It's a quintic polynomial hypersurface in projective space. Okay, and I know that that's quick, but so essentially what you're doing is you're writing down the D terms and you're writing down the F terms that you get by minimizing this thing. And you see you get these equations G5 of phi equals 0, and I didn't explain what G5 is, but it's a degree 5 homogeneous polynomial. Okay, so when you look at the D term, essentially it makes a P4 for you, the ambient space, and then when you look at the F terms, it cuts a hypersurface in that ambient space and gives you a quintic. Okay. And as R goes to infinity, it better and better approximates a nonlinear sigma model with the quintic as target. Okay, so that's the basic idea. And so now I'm just sort of, so you can do such a phase analysis in more detail, which is true even at the quantum mechanical level. And what you find is, so here is a P1, which, so this is the complexified Fi parameter space that I've just denoted as a sphere. And there's this, so this large volume point corresponds to the quintic that I just described. Now if you take the R goes to minus infinity limit, you'll realize that you have what is called the Landau-Ginsberg theory, which is non-geometric, but the Landau-Ginsberg theory is basically, like if you take the phi-4 theory and tune the mass to exactly 0, you get an interacting conformal field theory, and so that's what I mean. So it's a theory like that. So it doesn't have any geometric interpretation. And then there's a third singular point in the moduli space, which is the Coulomb branch. Okay. So if you analyze the GLSM, you get 3 singularities, and it's pretty cool. So if you analyze the nonlinear sigma model for the quintic Calabi, you get the same kind of moduli space. You have a thing with 3 singular points. You have a P1 with 3 singular points. Okay. So seeing this kind of a match is kind of a proof of the duality that I mentioned. So I told you that if you take the GLSM and the NLSM, they flow to the same theory. And what I'm plotting here is the moduli space, which is a property of the IR theory. And the fact that I see the same diagram in both cases is a proof of that.
But just because they flow to the same point doesn't mean that they are really equivalent quantum field theories, does it really?
Well, I mean, they are as far as the IR theory. So if you ask a detailed question about the UV physics, the two theories will differ.
Okay. Yes.
But if you ask a question only about the IR physics, which is what we're interested in,
the endpoint of the flow.
The endpoint of the flow. So then, you can use one or the other based on your convenience.
But how do I know their approach is the same? I mean, the endpoint is the same. I give you that.
Yeah.
But normally we are interested in corrections to that endpoint results, don't we?
Well, not me. Not me in this context.
But somebody else who might be.
Yeah, so then it'll be different. It'll be different.
Okay, fair
So it's just that locally away from the fixed point, you'll see the same deformations. Okay, but like if you follow it some finite distance on the RG flow, the theories will be different.
Okay.
Cool. So, so now, like about, I guess, almost 2 years ago now, people figured out how to calculate the partition function of these GLSMs. If you just put the GLSM on a two-sphere, you can calculate that path integral exactly if you have this much supersymmetry. Okay, so the full path integral of all the fields, and the technique that is used is called localization, and it uses the fact that there's a fermionic symmetry in the field space to make this path integral. You can turn this path integral into a saddle point calculation, and that saddle point calculation is exact. Okay, so I'm not going to go into details, but there are various checks of this calculation, and there's it passes all tests. So there's nothing funky going on. And so the result is that you can have any GLSM with an arbitrary gauge group, any kind of matter representation in Fi parameters, and you can calculate the two-sphere partition function. Okay, so I'm going to skip the slide because I'm not going to discuss the details of the calculation anyway. But so all I'm saying is, believe me that it can be exactly calculated. And this is what the formula looks like. Okay. So the formula is essentially a giant contour integral. Okay, that's all it is, and that is the feat of localization. We've turned an infinite dimensional integral into a finite dimensional contour integral. Okay, so these parameters sigma are essentially valued in the Cartan subalgebra of this group G, and this sum over M is basically a sum over the root lattice of G. And here you see evidence of the saddle point calculation. Okay, so this first term, Z classical, is basically a saddle point action. It's an exponential. Okay, and then there are one loop determinants, which for the gauge group involve a product over all the positive roots of G. And for the chiral fields, involve a ratio of gamma functions, okay? And that's because we use zeta function regularization. So, so the localization calculation makes this, makes the path integral into, makes it exactly equal to a free field calculation, and one loop determinants around the free field. So that's why the answer looks like that. Okay.
Is there a quick way to see that they are not corrections?
Say it again.
If there's a quick way to see that there are not corrections, then study them.
So the.
I mean it's being exact, so looks like a miracle. So why is it happening?
So the reason is there's this fermionic symmetry, and so what you do is you can take your original action. I guess I haven't put it on the slide. So you can take your original action and add to it a Q exact piece. Okay, and then so the parameter in front of that Q exact piece doesn't change anything. Okay, because it's Q exact, and then you can take that parameter to infinity. Okay, and then you can forget about your original action and compute the saddle point with respect to that parameter. So that's the saddle point parameter that you get. And so because you can actually take it to infinity, there's no. Right.
Is there a prescription given for what contour you take to do this final interval?
Yeah, so there is. So I haven't described it here because it's technical, but I'm happy to talk about it. Yeah, so it's not, and it's related to basically how you regulate these. Essentially you get something like product of L, okay, L going from 0 to infinity. So you want to regulate that product in some way, that infinite product. And so you write it in terms of a contour integral. You write it as a ratio of gamma functions. And so the contour prescription basically tells you exactly which poles you need to include to make your regularization scheme consistent. Yeah.
Very roughly, how does the clone branch assumption enter this calculation?
That's a good question. So it turns out that there's a choice. So what I have shown you here is the Coulomb branch, representation. But there's two ways in which you can do this localization calculation. One gives you a Coulomb branch answer, and the other gives you a Higgs branch answer.
If you go on transparency back, where you mentioned Coulomb, or was it here? No. Maybe one more. Sorry, no, I give up.
No, I think it's here.
No,
No.
There was a sphere. Oh, that's those ones. Yeah.
Yeah.
You see, this is a graph in psi space, and
Yeah.
this, and then you have a point there. It says Coulomb branch. Does that mean there is a particular value of psi? You're assuming?
No. So all these are great questions. So the value of psi depends on, so depending on the value of psi, you would close this contour in a different way. Okay, but this formula is, so this sigma here is completely independent of the actual Coulomb branch of the theory. So as part of the localization trick, you add some Q exact terms to your action. Okay, and so when you take that new action that you have, you're basically putting that GLSM on its Coulomb branch. So that's why you have some integral over here that's valued on the Coulomb branch. Okay, this is not a satisfactory answer in any case. I'm happy to talk after, but you know, it's so there's two ways in which you can do the calculation. One gives you a formula like this, and another gives you a sum over vortices, which are Higgs branch objects. Okay, but that is not useful for us. That's why I haven't written it down.
There are several parameters in the partition function to the one aren't you?
They don't, so that's a nice thing. So the parameters that show up are only the exactly marginal ones, like R and theta. Okay, so these are marginal parameters of the SCFT. So this partition function, which is calculated using the GLSM, is actually a property of the IRCFT.
So IRCFT has the same partition function as this one.
Yeah. And so then this is where the GLSM comes in. So you could do this calculation only because the kinetic terms in the UV are linear. Okay, in the NLSM you have nonlinear kinetic terms, so it's more challenging. Whereas here, you know, so essentially you can calculate what your saddle points are easily because you have a free theory.
So the idea is to compare this now with CFT or?
Yeah.
Yeah.
Yeah. So that's exactly what we did. So so we just calculated for a GLSM that flows to an SCFT, and this is what we found. So we found that if you take a GLSM for a Calabi X, this partition function essentially gives you e to the minus k, where k is the Kähler potential on the modular space. So this, and so okay, I've written it out here. So k is the Kähler potential since it's exact on the fully quantum corrected Kähler modular space of X. Okay. And you know, one can do a similar calculation for the complex structure one too. But you know, the way this partition function was calculated, you know, it kind of preserved one of the R symmetries and not the other, and that's why we're ending up with the Kähler modular space. And that's nice for us because this was the one that was challenging. Okay, so what we did, so we conjectured that this is true based on evidence that I'll show you in the next page, and Gomez and Lee were able to provide a physical argument as to why, you know, like a physics proof that that this GLSM partition function calculates the Kähler potential of the CFT.
What's the meaning of physics proof?
That's why I said argument first, and then by physics proof I mean that I can tell you what they did. I mean, they did a localization calculation on a squash sphere, and then they took the squashing parameter from 0 to infinity.
Oh, that doesn't make it physics. Doesn't make it physics argument, does
Maybe
it?
not a solid
As in,
example.
it assumes that things like path integrals and so on are rigorously defined. So if you make those assumptions, then it's a proof. But yeah, I mean, so they gave a strong argument as to why this should be correct. Like, I would say like somehow more general and stronger than the argument that we give. So relative to us, it's a proof, I guess. So what we did was very simple. We just calculated this thing for the GLSM, and we expanded e to the minus near a large volume point where we knew that a quintic, you know, where we knew that we should get the quintic. And then, you know, in general, if you had a Calabi nonlinear sigma model, e to the minus k takes this form. Okay, so now these n etas are the Gromov-Witten invariants. Okay, and this chi is the Euler character, and this is the perturbative correction that you get, and this is the classical piece. Okay, so t here is the Kähler modulus. And I know that I've been switching notation on you a lot, but you know, so t is the the Kähler modulus, which is related to the complexified Fi parameter in the GLSM. Okay. So here's what we did. So we calculated it, and then we found that when you expand this formula out in powers of t, or e to the 2 pi I t, okay, that these Gromov-Witten invariants actually match, so we calculated for many examples like the quintic and so on, and these Gromov-Witten invariants exactly match the known answers. So that's why we made this conjecture. Okay. Is the procedure clear on what we did? We just did the calculation and we expanded it. We took the GLSM for example, for the quintic. We calculated the partition function using the contour integral, and we expanded it as some kind of power series, and we were able to identify that these quantities are exactly the Gromov-Witten invariants. And so the partition function must be e to the minus k.
To read off Gromov-Witten invariants, you have some other expression already then given to you.
Yes,
what do you compare it with?
So people have calculated the Gromov-Witten invariants for the quintic mathematically, as well as using mirror symmetry. Okay, so we knew what to. So for example, the first one is 2875. So this is the number of rational curves of degree 0. The next number is 609250, and the list just goes on. And we were able to match the integers exactly. Okay, so that's why it gave us confidence that this conjecture is correct. And in fact, then there was a physical argument that showed that it should be the case. Okay. So, and just to flash some formulas, you can calculate that the partition function for the quintic GLSM, and this is exactly what it looks like. I have a residue integral, okay, and here I see a function sine 5 pi epsilon over sine to the 5th pi epsilon, and as epsilon goes to 0, you can see that there's a 4th order pole. Okay, so you just have to evaluate the residue around this 4th order pole for this formula. And once you do that, and you do like a bunch of other stuff, you see that you get the correct Gromov-Witten invariants, the correct Euler character for the quintic, and you see the right structure. So based on this, we made the conjecture, and it's been physics proved. Cool. So what is all this good for? Basically, if there's a Calabi manifold which I can build a GLSM for, then I can calculate various, there's this explicit formula for the partition function, and I can use that to calculate the exact metric on the moduli space, which means the kinetic terms of a type 2 compactification, and I can, from the math point of view, I can calculate all the Gromov-Witten invariants. Okay, so that's the summary of what I just discussed. And now part 2 of the talk was me wanting to go from, rather than starting with a Calabi, I just wanted to start with a GLSM and try to see if I can derive new Calabi-Yaos. Okay.
Just a quick question. Those are n equals 2 results in 4 dimensions.
Yes.
Is there a way to get n equals 1 results out of it by some methods, or is it a long shot? Do I have to start all over to do n is 1?
Yeah, so
there's no symmetry breaking, in other words. N to 2 goes to n is 1 that you're familiar with?
not that I'm familiar with, I have to think more about it, but I haven't yet.
For you, the buck stops here.
The buck stops here. Like I was kind of, that's going too physicsy for me.
All right, fair enough.
So I was interested in the Calabi and the n equals 2 stuff. But that's a good question, and somebody knows the answer. Okay, so let me just think for a second. Okay, so in this section, what I want to talk about is how you can start with a GLSM and try to derive new Calabi-Yaos. Okay, so so now there's naturally a question: which Calabi-Yaos have a GLSM description? Now it's true that every Calabi-Yau threefold is an algebraic variety, and what that means is it can be written as the zero locus of polynomial equations in a projective space. Okay, so this is true for all compact Calabi-Yau threefolds. You can always write it this way. Okay. Now, such a variety is called a complete intersection if the number of equations that you have is equal to the dimension of the ambient space minus 3. Okay, so basically, if there are 3 equations and each equation is independently cutting down a dimension, it's called a complete intersection. Okay, so that's in some sense simple. Okay, so is that clear? So so now, okay, these are complete intersections, and we know how to construct GLSMs for any Calabi that has such a presentation. So now you can ask the question: are all Calabi manifolds complete intersections? And it's not true. It's fantastically not true. So let me just quickly go through this slide. And actually, rather than going through this slide, let me give you an example, because I wanna skip ahead. So let's say I defined an algebraic variety in the following way. Okay, I take a 4x4 matrix, okay, which has 16 components. Okay, and imagine that each component is a coordinate in some projective space. Okay, so because it has 16 of them, we're living in P15, okay, in CP15. And now I define the Calabi, or I define the variety as the rank less than or equal to 2 locus. As the matrix rank less than or equal to 2 locus inside P15. Okay, so now we can just do a simple degree of freedom count. Okay, so if I had a rank, let me just say equal, if I had a rank 2 matrix, it means that I have sort of 2 linearly independent rows. Okay, so there are 8 parameters because there are 2 linearly independent rows, and the third row should be a linear combination of these 2. So that's plus 2. And the 4th row must be a linear combination again of these 2. So that's 2. So any rank 2 4x4 matrix has 12 degrees of freedom. Okay? The total number of degrees of freedom is 16. Right? So this locus is basically a codimension for locus inside P15. Okay, because this rank 2 condition ate away 4 parameters. Okay, so it's codimension 4, but you can ask how many equations do I need to, let's say I want to write polynomial equations describing a rank 2 locus. Okay, the way I would do it is by setting all 3x3 minors to 0. Okay, so a matrix has rank 2 if every 3x3 minor is 0. Right? And you can ask how many 3x3 minors are there, and there are 16. Okay, so now we see that the number of equations is 16, but the codimension is only 4. And so this is really not a complete intersection. Complete intersection is when you can enforce the codimension by independent equations, okay, by exactly that number. So here's a simple example of something which is not a complete intersection. And then you can ask, do these capture all the non-complete intersections? And that's also not true. Okay, so really a lot of it is unknown. And so, so I just wanted to say very quickly that, Calabi-Yaos of this type are called determinantal varieties because it's a rank condition on a matrix. And Hori and Tong were the first ones to write down a GLSM to describe such non-complete intersections, and we extended their work and made it more general. And so we know now how to write GLSMs for these things. Okay? But still, this is just scraping the surface. And we don't really know. Yeah, go.
Sorry, these 16 equations, they're just not independent.
Yes.
But isn't there at least locally a way to write an independent subset?
Yeah, only locally. That's the problem. So yeah, so locally I can always find four minors whose vanishing implies the vanishing of all the other 12. Okay, but I can do that only locally because on a different patch I would need to use a different 4. So that's the problem. So I need the full set to describe the entire compact Calabi-Yau threefold. That's a good question. And so yeah, so that's what I've discussed here. More generally, you have, so this is called the syzygy, SY, ZY, GY. And it refers to the relations amongst these equations. Okay? And generally, you have some equations, they have relations, those relations have relations, and so on. Okay, so there's a huge structure that exists, which you can analyze and determine, for example, that the codimension is 4. Cool. So let me just skip this and let me just show you this picture. So here's a Venn diagram of all Calabi-Yau threefolds, and these are the complete intersection ones, which we definitely know how to describe and we've learned a lot about. And then there's this yellow circle of Glsm Calabi-Yau manifolds, which is what we would like to explore. Okay. And here was like a simple idea we used to try and chip away at that question. Okay. So our idea was basically you take a very general gauge linear sigma model with some groups, some Fi parameters and matter, and you enforce the following conditions. Okay, so you say that U1 vector and U1 axial is a good symmetry, and that imposes some conditions. And then you demand that the R charge of all gauge invariant operators be even positive integers. Okay, so what we're trying to do is to make the GLSM as close to an NLSM as we can. Okay? So we're taking all the NLSM properties that are easy to enforce and enforcing them on the GLSM. And next, we will make the complex central charge equal to 3, which is the dimension of a Calabi-Yau threefold. So this puts another condition on this gauge group and matter. Okay? And this gives us a large family of n equals 2, 2 SCFTs. And using the partition function, and all this is very well known, but what we did was, we are interested in answering this question. The GLSM flows to some SCFT, and this orange thing is the SCFT moduli space. And let's assume we had a singular point in that moduli space, which is located at when the Fi parameters go to infinity. Okay, so this is the moduli space of Fi parameters. And so we want to ask whether that singular point, or that neighborhood of that singular point, can be described by a nonlinear sigma model or not. Right, so ahead of time, we don't have a Calabi-Yau in mind. We just write on a random GLSM, and we're interested in whether a singular point corresponds to a geometry or not. That's the flavor of the question. And so our basic idea was, since we had been computing partition functions for many months now, we'd gotten very good at it, and so we had the following idea: if that point is a large volume point or a geometry, then it must have the same asymptotics as a Calabi-Yau does. Okay? So remember that ZS2 is nothing but the Kähler potential, or e to the minus Kähler potential. And if I had a classical geometry, then e to the minus k is basically the volume as a function of Kähler parameters. Okay, and it's integral j wedge j wedge j. Okay, and you might be familiar of this thing from like supergravity, where the Kähler potential is generally minus log v, where v is the volume. Right. So this is the classical result. So we have the full quantum answer, and we want to enforce that asymptotically, as you go closer and closer to the nonlinear sigma model, all the instanton corrections should die, and you should have this log cubed structure. Okay, so we turned this problem into a problem of complex analysis. So write down the partition function, look at the poles, and try to see whether you can, under what conditions you see this structure. Okay? So this, again, I stress, is a set of necessary conditions. So conditions 1 through 4 are a set of necessary conditions for a GLSM, for a singular point of a GLSM to be geometric. And we considered a random GLSM, the simplest one that we could construct, that satisfied all 4 properties and didn't obviously look like a Calabi-Yau GLSM. Okay? So here it is. The gauge group is U1 times Z2, and there are 4 fields of charge +1 and 1 field of charge -4. Okay, so if you blindly looked at this, you might have thought that this describes a K3 surface. Okay? But the key is we used a different superpotential. So we used the superpotential p squared times G8. Okay, so what I want to stress is this GLSM doesn't obviously correspond to any kind of geometry. It's just some SCFT. Okay. And now the Z2 gauging is important. It's the Z2 gauging that allows you to satisfy this condition, that the R charge of all gauge-invariant operators be even positive integers. So this is a GLSM that satisfies all these conditions. And we tried to study what the phases of this GLSM are as you make the Fi parameters large, or the singular points. Again, I'm not going to go through the analysis. I'm happy to do it after an hour.
So again, if it satisfies all these conditions, then it corresponds to a Calabi also.
No, we don't know. So
Oh,
we
you
wanted,
don't know.
so it's a set of necessary conditions. Okay, and I have counterexamples to show you that it's not actually sufficient. So I have a GLSM that it looks like it should be a Calabi, but actually it isn't.
So how do you know that you're advancing into non-killer manifolds, for example, that you can describe this GLSM?
Because of, well, yeah, because of 2-2.
So it's determined already, right?
Yeah. I wanted to say that, but I wasn't sure suddenly.
But 2-2 is fixed now by these conditions, yeah? Or how do you know?
I'm starting with 2-2, and you mentioned it.
Okay.
Yeah.
Okay.
Yeah. So, so again, I'm skipping through the details, but I'm happy to go through it after if you're interested. But, one of the phases of this GLSM is just a Landau-Ginsberg theory. And the other phase has this interesting structure. It's a hybrid phase, which Ilaria knows a lot about. It's a hybrid phase, and it kind of looks like two copies of P3, okay, that are glued together. And the reason there's this gray blob is that there's no way to geometrically represent it. There's a Landau-Ginsberg theory living there. And so, basically the moduli space looks like two copies of P3. But as the two copies of P3 approach each other, okay, you get a Landau-Ginsberg model. Okay, it looks weird. It doesn't obviously look geometric at all. Okay. So what we were able to show is that this hybrid phase is actually a geometry. Okay, and let me just quickly take you through the argument. So the first thing we noticed is that the partition function of this hybrid phase is the same as the partition function of a degree 8 hypersurface in P11114. Okay, so that was curious. Okay, and then it's also interesting that this octic hypersurface, if you tune its complex structure parameters, is a double cover of P3 that is branched over an octic. Okay, and you can just tune it. I can again show you the details after. And so that kind of looks a lot like this picture, but obviously is not a proof. And so here's how we gave a physics proof. I guess Ergid isn't around, so it was physics proof. So what we did was we constructed a second GLSM, which had gauge group U1 times U1, and this superpotential, and this field structure. And this GLSM2 was basically a GLSM written for this hypersurface when you resolve the ambient space. So imagine, so this is a singular ambient space. So you blow it up, and then you get a toric variety that has two parameters. Okay, so that's why I have two U1s here. And this is GLSM2. Okay, so here's what we did now with GLSM2. You consider its phase diagram, and then you see that it has three phases. One is the hybrid phase, which is what we encountered earlier, the mysterious one, which we didn't understand. There's another phase which is purely geometric. And this geometric phase is the double cover. It's like a degree 8 hypersurface in P11114. And then there's this Landau-Ginsberg phase. Again, the same Landau-Ginsberg phase which we saw in our first model that we wrote down, the U1 times Z2 model. Okay? So that was cool because we don't understand this phase. We think it might be this one, but at least we see them all in a single theory. Okay? So now here's the argument. Now the two Fi parameters of GLSM2, there are two U1s. One of them corresponds to the overall size of this projective space. And the second Fi parameter corresponds to the blow-up, the size of the blow-up. Okay? But the octic hypersurface doesn't even pass through the singularity. Okay, so this degree 8 hypersurface in P1114, it misses it, like the codimension doesn't work out, so it misses the singular point. So really, the IR physics should be independent of one combination of those two Fi parameters. Okay, and that's because the hypersurface doesn't even go through the singular point. And the second Fi parameter is just resolving that singularity. But the GLSM, what it does is it entangles them. And so we don't know which combination is relevant in the IR and which one just disappears in the IR. And so to figure out which one it was, we again calculated the partition function. And we found that the partition function only depends on this combination. So Z1 and Z2 are the exponentiated Fi parameters. So it only depends on those two. And so then we saw that now if you plot all the points, you can plot lines of constant W. Okay? And lines of constant W are lines where the physics is the same. Okay, or nothing changes because it's a fake parameter. And so we beautifully see that there is a single line, which is W equals 0, which connects both the geometric phase and the hybrid phase that we didn't understand. Okay, so so these contours that I've drawn are contours in GLSM2, and in order to get the phase diagram, of this theory, all you have to do is project this thing down. So along each contour, nothing changes. That's what I just argued to you. And so if you collapse the diagram down, you'll realize that the geometric phase and the hybrid phase are just simply connected, so they're identical. Okay, so this was an argument now that physics proves that the geometric phase is that the hybrid phase is secretly a geometry. Okay, but it happened to be a known geometry. It happened to be a geometry that we already know. It's a double cover of P3 branch over an optic. And so essentially, what we feel is that, let me just summarize. We give 4 necessary conditions for a GLSM to have a geometric phase. And this U1 times Z2 GLSM, it satisfies these 4 conditions, but if you look closely at the phase structure, it looks mysterious. There's a Landau-Ginsberg and a hybrid phase. And then we were able to give arguments that this hybrid phase is actually a known Calabi geometry. It's a double cover of P3 branch over an optic. Again, and we did so by constructing an auxiliary GLSM, which had 2 parameters, but one of them didn't really matter. And people were confused, but I'm happy to take questions. Let me just conclude because I'm running out of time.
So that was supposed to be now a new Calabi.
No, that's so good. So that's a new realization of a known Calabi manifold.
Okay.
Okay, but what we want to do is basically, my last part of my conclusion, use these 4 criteria. So the first 3 criteria are already known, but we want to use the asymptotics of the partition function as a criteria to generate more examples like the U1 cross Z2 theory. And the hope is that doing that, so firstly, you can try to systematically enumerate such GLSMs. Take U1 times a simple group, okay, and then try to understand what representations and what choices of representations and R charges can give you possibly a large volume. So even that has not been done. And what I hope is that then you can get a set of candidates, okay, that could be large volume parts. And then you can analyze those GLSMs in greater detail, and hopefully you can come up with new constructions of Calabi manifolds that are not already known. And then, I just summarized the rest of the talk. So I'll end here. Thank you.
So do you have further questions for Vijay? All right, if not, let's thank him again.
Thank you.